Two vectors lie flat in the plane, multiply them with the cross product, and the answer points straight out of that plane into a third dimension. This operation drives torque, angular momentum, and magnetic force. Today we define its magnitude, find its direction with the right-hand rule, and establish its algebraic properties. Take two vectors, A and B. Any two non-parallel vectors form a plane, and theta is the angle between them. The magnitude of the cross product across B equals the magnitude of A times the magnitude of B times the sine of theta. We restrict theta to the range from 0 to pi. That restriction guarantees the sine of theta is never negative, so the magnitude is never negative. Notice the contrast with the dot product, which uses cosine and returns a scalar. The cross product returns a vector. The magnitude is only half the definition. The cross product is a vector, so it needs a direction. The vectors A and B form a plane, and the cross product points perpendicular to that plane. But there are two perpendicular directions, one out of each side. We need a convention to pick one. That convention is the right-hand rule, and it makes the choice the same way every time. Here's the construction. First, redraw A and B so their tails touch. Then draw an arc starting at vector A and finishing at vector B. Now curl the fingers of your right hand the same way as that arc from A toward B. Your right thumb points in the direction of A cross B. Call the result C. It rises perpendicular to the plane containing A and B. The order matters. The arc goes from the first vector to the second. Always remember the direction of A cross B is perpendicular to the plane formed by A and B. The magnitude has a clean geometric meaning. Group the formula as the magnitude of A times the quantity magnitude of B times sine theta. The vectors A and B span a parallelogram. The term magnitude of B times sine theta is the projection of B in the direction perpendicular to A. That projection is the height of the parallelogram, and the magnitude of A is its base. Area equals base times height. So the magnitude of A cross B equals the area of the parallelogram the two vectors span. A bigger angle, up to 90 degrees, means more area and a larger cross product. The grouping works the other way too. Write the magnitude of the cross product as the quantity, magnitude of A times sin theta, all times the magnitude of B. Now the term magnitude of A times sin theta is the projection of A in the direction perpendicular to B. That projection becomes the height, and the magnitude of B becomes the base. It's the same parallelogram with the same area. Either vector can serve as the base, and the magnitude of the cross product doesn't change. Here's an important special case. Parallel or anti-parallel vectors. If the two vectors point the same way, then theta is 0 and the sine of 0 is 0. If they point in opposite directions, then theta is pi, and the sine of pi is also 0. Either way, the cross product vanishes completely. Geometrically, this makes sense. The parallelogram collapses down to a single line with 0 area, and the two parallel vectors share no unique component perpendicular to their common direction. As a direct consequence, any vector crossed with itself is always 0. Now the algebraic properties. First, order matters. The cross product is anticommutative. A cross B equals negative B cross A. Here's why. Reverse the order, and the right-hand rule arc now sweeps from B to A instead of A to B. Curl your fingers the opposite way, and your thumb flips to point in the opposite direction. The magnitude stays the same, the direction reverses. This is a sharp contrast with ordinary multiplication and with the dot product, both of which are commutative. With cross products, never swap the order casually. Two more properties. First, scalars factor out. For a scalar C, the quantity C times A crossed with B equals C times the quantity A cross B. Likewise, A crossed with C times B equals C times A cross B. So scaling either vector scales the whole product. Second, the cross product distributes over vector addition. The quantity A plus B crossed with C equals A cross C plus B cross C. Similarly, A crossed with the quantity B plus C equals A cross B plus A cross C. These rules let us expand cross products of sums term by term, just like ordinary algebra. Here's the complete picture. The cross product of A and B is a vector. Its magnitude is the magnitude of A times the magnitude of B times sine of theta, which equals the area of the parallelogram the two vectors span. Its direction is perpendicular to their plane, chosen by curling your right hand from A toward B and following your thumb. Parallel or anti-parallel vectors give 0 because the parallelogram collapses. Swapping the order flips the sign. Scalars pull out and the product distributes over sums. With the geometry and algebra in hand, the next step is computing cross products component by component, decomposing vectors in Cartesian coordinates with unit vectors. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.